Okay, we'll get started. So there will be no attendance from today onwards. So you guys are free to attend the class, truly free to attend the class. Uh, in the previous class, I made a small mistake, so I wanted to correct that particular mistake. So, one of the thing that we were talking about was proof by proving the contrapositive statement or proof by contradiction. So I kind of mixed it up. So I wanted to make that clear. So contrapositive statement. So what's a contrapositive statement? So let's say we want to prove that A implies B. This statement is equivalent to saying not B implies not A. And this statement is known as contrapositive statement. And the contrapositive statement is a completely reasonable statement to make. Proof by contradiction is A and not B leads to contradiction. And this is the proof that I generally don't like. So if I can prove using contrapositive, I'm happy. If I can prove the statement, I'm happy. If I'm proving contrapositive, I'm happy. If I'm proving by contradiction, I'm generally not happy. And then I try to think about how can I use this argument to come up with a contrapositive statement and prove the contrapositive statement. So applying this thing, what we wanted to show was integral of norm of f fx square or ft square dt this goes from a to b. This is equal to 0 implies that f is equal to 0. This is what I want to prove. The contrapositive statement is if f is not equal to 0, then this implies that this is not equal to 0. Right? This is a contrapositive statement. And this is what we want to prove. Okay, this was so to remind you, we were discussing about norm, and we said that this is a valid norm with a square root. It's a valid norm on CAB to Rn. And so what we wanted to prove was the first statement, which is that if the norm is equal to 0, then the function itself has to be equal to 0. That's where we stopped in the previous class. And now today, what I'm talking about is contrapositive. Let's try to prove the we don't have to prove it, but the contrapositive statement is if f is not equal to 0 and f is a continuous function, then the squared norm integral is going to be non-zero. So is this statement obvious? If f is non-zero and a continuous function, then this particular integral will be non-zero. Is that an obvious statement? If f is not equal to 0, why should the integral of norm square be non-zero? Can someone think about that and give me an argument? Why should this statement be true? We want to prove this statement. We said, well, I don't know how to prove this statement, but perhaps I can prove the contrapositive statement. So not B is equal to not A. So not B implies not A. So this is my not B. This is my not A. If I can prove that statement, then it also proves this particular statement. So now the question remains that if I have a non-zero continuous function and I do this integral, why should it be non-zero? Anybody wants to give it a shot? Yes, please.
So something to do with the fact that that magnitude squared is positive.
Right, so this is positive definite, but now we are taking an integral. So we have a non-zero function, we are taking the integral. We want to actually prove that that this integral is going to be non-zero.
Right.
So what's the argument to prove this particular statement? Anybody has heard of epsilon delta definitions? Epsilon delta? No? What's a continuous function? So f is continuous. Let's say f is continuous at x or at t naught if and only if for every epsilon greater than 0 there exists a delta greater than 0 such that f of t minus f of t naught is less than epsilon for every t minus t naught less than delta. For every t such that t minus t naught is less than delta. And I probably want to put a norm here because f right? This is the definition of continuity. I'm pretty sure you've seen it before in your calculus class. And so now we know that this particular function, originally our vector space was the space of continuous functions from the interval ab to Rn. So if this is true, how can I prove that this integral is going to be non-zero? So here is the argument. So let's say assume t naught in AB pick epsilon greater than 0 and delta be such that let me pick okay. So remember that f is non-zero, so I can always pick a value t naught in this interval such that f of t naught is not equal to 0, and then I'm going to pick epsilon equals to norm of f t naught, which is greater than 0. Then pick delta f of t naught minus f of t is less than epsilon over 2. What should the next step be? Any idea what should I do next? So I want to prove that this integral is non-zero. What can we do next? So I have integral a to b norm of ft square dt is greater than equal to integral t minus t naught less than delta t is in AB norm of ft square dt, and this is greater than epsilon over 2 square. So ft in this interval is less than perfect. So this thing, the norm of ft within this particular interval must be greater than epsilon over 2, because ft naught is epsilon. This norm is equal to epsilon, and this is less than epsilon over 2. So therefore this must be greater than epsilon over 2. So I did the square, and this gets multiplied by delta over 2. Which is greater than 0. So therefore the integral is non-zero. Okay, that's one way to prove the statement that the square root of this is positive definite, which means that if this integral is equal to 0, then f must be necessarily 0, because if f is non-zero, I can show that the integral is going to be non-zero as well. So that's the contrapositive statement. So this is proof by proving the contrapositive statement. I just wanted to show you, I mean, we don't have to do it for all different norms, but I just wanted to show you that this is typically how a proof would work to demonstrate that something is a norm or not a norm. The other thing that we did not demonstrate so far is the triangle inequality. So that's a beast of its own, to prove that a certain norm that you have picked satisfies the triangle inequality. But you know, we have given you enough examples, and I'm sure you've seen it in other classes as well. And there are many books written on the classes of norms that satisfies triangle inequality. So we'll just refer to those books as and when needed. Okay, any questions so far? So far, what all things have we done? We have learned about fields, we have learned about vector spaces, linear vector spaces. We have learned about linear operators over linear vector spaces. We have learned about norms on linear vector spaces. When you have a linear vector space, you add a norm to that particular space, it becomes a normed vector space. Okay, so this continuous functions with this particular norm, I mean not this norm, but this norm is actually a normed vector space. Okay, so linear vector space with a norm is a normed vector space. Any questions so far? Okay. Now we'll talk about operator norm, the norm of a linear operator. So that's the last thing that I have to do in the preliminaries before we get into the discussions about the linear systems. So let's study that. So I have a V to W. So V normed vector space, and then W. This is another normed vector space. So the operator norm A, sometimes they don't put V and W, but I'm going to put V and W today just for the sake of clarity. But generally speaking, from the context, it will be clear what norm we are taking, and we'll be using those norms in the rest of the semester. What is this? This is supremum over all AV such that norm of V is equal to 1. Okay, I want to give you a pictorial view of what this matrix now. I mean, in the context of matrix, I'll give you the a simple way to understand what this matrix norm is going to look like. But this definition is general. It's true for any any pair of normed vector spaces. Oh, this needs to be a linear operator. So A is a linear operator between two normed spaces. Okay. So let's think about it. So let's say my operator A is a matrix in R2 cross 2, V equals to R2 with the usual Euclidean norm, and W is also R2 with the usual Euclidean norm, L2 norm, Euclidean norm, the typical norm that we know in R2. What does A do to a sphere? So this is the unit sphere or unit circle in R2. So R2 you call it a unit circle, but in Rn it will be a unit sphere. So I have this unit sphere in R2. This is my norm of V equals to 1. What happens when I multiply this matrix A to this a vector within this unit circle? Anyone remembers what happens when you multiply the matrix to this circle? It kind of stretches the circle in some dimension and it compresses the circle in other dimension. So under the operator A, this is going to look something like this. This is your AV. Okay. So what does A do? A stretches and compresses this unit circle along different directions. So depending on which direction you are looking at, it will be stretching it or compressing it. And then you look at the maximum distance of this. So this particular thing, this distance is the norm of A. This distance from here to here, that's norm of A. That's the way to think about it in Rn. It's with Euclidean distance, I think it becomes extremely easy to imagine what this operator norm is going to look like. However, note that this norm is actually defined more generally for linear operators over infinite dimensional spaces. So let's look at an operator A that goes from CABR to CABR, which is given by ABT integral A to B. Let me use capital H ST BS DS, or maybe HTS. So this is a linear operator. Why is it a linear operator? Well, AV1 plus V2 equals to AV1 plus AV2 and A alpha B equals to alpha AB. So both these conditions are satisfied by this definition of the operator, and therefore it's a linear operator. Okay, you have seen this linear operator in your signals and systems class and in your Laplace transform class 3551 feedback control systems. Typically there, instead of going from CAB to C, we were actually going from the space of continuous functions to the space of Fourier transforms or Laplace transforms. So rational polynomials over a complex plane with a complex field, whereas this one was real valued signals. And I think in higher, maybe in like 5,000 level signal processing classes, you go to like the complex signals as well, signals that have a amplitude and a phase. I think the people in electromagnetics and so on, they use those kind of signals. So there, this one is also not a continuous function from AB to R, but it could be like a complex signal, and this would be the Fourier transform space. Okay, and this used to be in the Laplace transform. This is e raised to minus st actually. So in the Laplace transform case, it's something like this. In the Fourier transform case, it's e raised to minus j omega t or j omega t, depending on whether you are taking Fourier transform or inverse Fourier transform. So all of this is something that you have seen. We are just studying the generalization of all those ideas. I do want to note here that these spaces are different when you're talking about Fourier transform and Laplace transform. So this one is, the one that I've written on the board is from continuous functions to continuous functions, but in the Laplace and Fourier case, it's continuous functions to integrable functions on the frequency domain. So it's slightly different space than what I've written on the board. So this is a linear operator, and you can define the norm of this particular linear operator using this definition. Now, I don't know when we will need that, so I'm not going to compute the norm of this particular linear operator, because it depends on what is the norm we are endowing this particular spaces with. But when the time comes, we'll do the calculation for the linear operators that are of interest, once we know exactly what norm these functions are going to have. Okay, any questions so far on this? Okay. So far we have done fields, vector spaces, linear vector spaces, operators, operator norms, norms on linear vector spaces, right? So now we are going to delve into dynamical systems. Okay. Anybody who has taken a course in a class in differential equations before? Differential equations? No. Okay. Kind of, sort of. Okay. Uh, so that will be the topic for maybe 1 or 2 classes. Okay. So I want to go back to 1500s. Okay. So we are sitting in a classroom in 1500 AD. We're looking at sun, moon, stars, all of that stuff all day long, all night long. And we are looking at things moving. So sometimes, I mean, not sometimes, every day in the morning, sun comes up from the east, it sets in the west. And we see like a North Star, which is always at the same spot in the sky. And then we have other stars and constellations and so on and so forth, and they're moving around, right? So there are people like Copernicus, Kepler, Newton, and so on. They all noted what star they saw at what point of time during the day, what happened, and so on. So they created data set. They had a data set. It wasn't big data, it was small data, but they had data about where the stars are, where the moon is, what's happening with the tide, and so on and so forth. What did they do with the data? Anyone wants to take a wild guess? So they've collected this data. They have like a spreadsheet, the 1500 AD version of the spreadsheet, where they had noted down sun this time, moon this time, it's this location. What did they do with all that data set? Yes.
They probably calculated the orbits first before maybe trying to look at some kind of generalized model based off of that.
Wonderful, wonderful. So they wanted to predict the orbit. And so they wanted, in order to predict the orbit, they wanted to come up with a generalized model. What else?
I was going to say the same thing, right? The trajectory.
Right. So they wanted to compute the trajectory, and which is basically they wanted to figure out, they wanted to be able to predict the system, and they want to predict that particular system very reliably. And now prior to 1500, what was the typical model of the world? Earth is the center of the universe. The entire universe rotates around Earth, right? And then they came up with that particular model did not explain many of the phenomena that they observed on a day-to-day basis. And so they needed to come up with a different model, a model that is able to reliably predict how the world is going to behave 5 years, 10 years, 5 days, 10 days down the line, right? So they had data. They fed this data and they concocted a system model. In order to come up with the system model, they definitely needed knowledge from physics, chemistry. It depends on what field you are in, but you will try to pick ideas from physics, chemistry, biology in order to create the system model. So you have tumor data for cancer. You use biology, how the blood flows in the body, how the tissue reacts to the blood flow, how the tissue reacts to how the cancerous tissue reacts to the white blood cells, and so on. So you have all that information from biology. You look at the cancer as the growth of tumor, and then you come up with a system model. And I was looking at a book on this tumor model. There are like 20 models of how the tumor evolves in a cancerous cell. Okay, so they come up with a system model. Sometimes the system model could be extremely complicated and difficult. So they come up with an approximate model. And then using this approximate model, they do either control design or they do system design. right? This part of the spectrum, we are not going to study it in this class, but I'm sure you have taken enough courses in robotics, physics, chemistry, classical mechanics, quantum mechanics, electromagnetic waves, and whatnot to figure out how to use data to create a system model. So this is taught in other classes. This part, how to get approximate model from the system model, that's an art. I think this art is very, very field dependent and dependent on the kind of phenomena you want to capture with the approximate model. So to give you an example, I'm driving a vehicle. There's a lot of stuff happening in the vehicle. There is air is pumped inside the engine. There is fuel pumped into the engine, and then the entire thing is detonated, and then that creates a propulsion, and then that drives the gears, and then that drives the car. So that's the original system model. But in order for me to drive the car, I don't need to know all the system model. All I need to know is if I press the accelerator, it's going to accelerate. If I press the brake, it's going to stop. And if I steer, it's going to move around, like the vehicle will change its heading. And that's the approximate model I have in my head. I don't have to figure out what the engine RPM is, what the fuel air ratio is in the engine, how much fuel is being pumped, and all of that stuff. Like all of that stuff is something that is happening within the system, but I'm happy with an approximate model because I just need to drive the car and get home as soon as possible. So that's my approximate model. That model is in my head, but I don't have the system model. So depending on the situation, you want to have the appropriate model of the system to be able to solve the problem that is of interest to you. And what's the problem that is of interest to you? Either I want to design a controller, I want to design a system, or I want to predict behavior of that particular system. Okay. Any questions so far? Does this sound familiar? So this is the part that we will be interested in this class. So we'll try to do control design, system design, predict behavior, and so on using the approximate model that we might be interested in.
The linear system course, if like when I'm considering the model of say x equals the p vector, like an approximate model, is it for always be some kind of linear projection, or
We will be doing linear projection, yeah. I don't know what you mean by linear projection, but we'll linearize the model around the trajectory and we'll study that particular model.
what I had in my mind was that A transpose times A inverse times A transpose B.
That's a very specific kind of projection, but that's in the linear setting already. So we are looking at a functional equation, x dot equals to f of xt, and we want to linearize that particular system. So that is our original system model. We'll linearize it. That will give us an approximate system model, and we'll study the approximate system model for the rest of the class. I mean, for the rest of the semester, and we'll do control design, observer design, and so on in order to better predict behavior of that particular system. There is another complexity I wanted to outline here. Many a times the data is in the form of input-output data. Okay, so you provide an input to the system and then there is an output, you observe the output, and that allows you to come up with a system model. You know what the problem with this approach is? That the output could be much lower dimensional than what the internal states of the system are going to be. Okay, so what's an internal state? How do we, like, what's an easy example for this? So let's look at our body. So that's our system. What is the input to our body? The food that we eat, the air that we breathe, the exercise and the kind of information we consume, the exercise we do, that's the input to the system. And what is the output? We have a headache, or we don't have a headache, or we have stomach ache, or we don't have stomach ache, or we have fever, or we don't have fever. So that's the kind of output we are seeing. What about the internal states of the system? What about our blood pressure? What about our pulse rate and things like that, right? So those are the internal states of the system. Some of them are easy to measure, like pulse rate, you can just measure it right now. Some of them are somewhat difficult to measure, like blood pressure or HbA1c, how much blood glucose you have in your blood. And some of them are extremely difficult to measure. I don't know how good my kidney is. I'm about approaching 40 years old. I don't know how good my kidney is. I don't know how good my heart is. And even if I were to measure it, I don't even know how to measure it. And I'm not sure if somebody else can measure it and tell me that, okay, your heart is like 90% good or 90% bad or something like that, right? So there are many internal states of the system that I know that it exists. There's no way to measure that particular state. So the output that I see, which is the fever, the body temperature, the pulse rate, and so on, is actually very small set of states that I can observe. And there are a lot of internal processes within the system that I'm not able to observe, and therefore I don't even know what that dynamics is going to look like. Okay, so this is an important problem, and we will come back to this particular problem again and again throughout the lecture, because many a times when you want to do control design, all you have is output. And based on that output, you need to figure out what the next input is going to be. And so without knowing the internal states of the system. And so we'll have to figure out how to solve problems of those type. And we'll touch upon this subject maybe in March or early April. But it's something we'll be talking about throughout the class. Another example that I can give you, like more of a high level example that I can give you. So Newton came up with these laws of gravitation and whatnot, and many people studied the laws of gravitation. But then later on, people realized that, well, gravitation works for celestial bodies, like very large bodies. But when you go to atomic level, you don't necessarily just have gravitational waves, or gravitational pull. You have electrostatic interaction, you have other sort of interactions as well. And so this whole new area of quantum mechanics developed, because you could predict where the planets are going to be in the future, but you couldn't predict where the electrons are going to be in the future. And so the laws of gravity does not work at the quantum mechanics level. And so people came up with all kinds of crazy theories in 1800s and 1900s. And hopefully now we have a good idea of how electrons and neutrons work inside a thing at the atomic level. But right now, I think the current problems in like 21st century problem is that we have a lot of healthcare data, and we need to figure out what the system model for human health looks like. And that science is still evolving. Okay, so we are at 1500s of human body at this point of time, right? So just something to keep in mind. Okay. Another example for this is, if you look at lithium-ion batteries, what are the two things you can measure? The current, the input is the current, the output is the voltage. Those are the two things you can measure. Internally, there's a lot of degradation that is happening in electrolyte, degradation happening in membranes, degradation happening on cathode and anode material within the batteries, but you cannot measure it. There's no way to know what's happening to the battery unless you actually break down the battery and look at it internally, right? So the only way to know about the system is to dissect the system, but otherwise the only input you know is the current, the only output you see is the voltage. That's it. and you need to figure out what's happening inside the system. That's also an open problem, by the way, at this point of time. We don't know how that works. Or some people know how that works, but it's still something that's evolving. Okay, so what's a general model? So a lot of people have thought about it for a very long time. And so this is a general model that almost everyone agrees with, which is continuous time. So I'm giving the continuous time version, finite dimensional. Dynamical system. So that's the model. It says x dot I t. Everyone knows this dot notation, its derivative with respect to time is equal to fi t x1 t xn t u1 t umt yjt gjt. Okay, so continuous time finite dimensional dynamical systems. There are of course other variations. There is discrete time finite dimensional dynamical system. There is continuous time infinite dimensional dynamical systems. There are nonlinear dynamical systems and so on and so forth. But this is the one that we will be, we'll make it much simpler in the course of this semester. But this is the class of problems that we are interested in this particular class. So we have a bunch of internal states of the system, which we will collectively call as the state vector. We have a bunch of control inputs. We'll call it input vector or control vector. So I tend to use the word control vector, but depending on the papers/books, some of them will call it input vector. And then there is YT, which is the observation vector or output vector. This is something that you can actually observe based on some measurement device that you might have. And T is the typical time. Fi is known as the state transition function. Gj is known as the observation function. Okay? Yes?
I was wondering if there's ever any case where GI of T is nonlinear, phi of T is linear, or we not deal with those?
This one is linear, this one is nonlinear. See, I don't know about the linearity of Fi, but there are a lot of cases where Gj would be nonlinear, and then you have to invert it to figure out something of interest. So for instance, in the case of, let's say thermometer, where you are trying to measure what the temperature is, right? Typically speaking, thermometer is sort of linear in, if you have a small temperature range, like, human body temperature range, you kind of have this linear relationship between the expansion of mercury and the body temperature. But if you're looking at thermometer that is going to measure a very big range of temperature, then of course there are nonlinearities that kicks in, and then you need to be careful about those nonlinearities. Other sort of nonlinearities that happen is saturation. In many cases where beyond a certain reading, it just cannot measure, the sensor will not be able to measure. So your Yj of T will become constant. It doesn't mean that the observation is constant, but the state is still increasing. Yes?
So like, can you make this really important for the problem that X is the state, Y is the, U is the action, and Y is the mode?
Not Y is not the reward, but Y is the, so I know you're talking about reinforcement learning. I taught a class last semester on that. But generally speaking, that is studied under the umbrella of POM-DPs, partially observable Markov decision processes. So within RL, that's a very small subclass of problems that people study. We are not talking about the reward function / cost function here. I'm not sure if it is, if we are doing any optimization in this class. It doesn't seem like this book has optimization. Oh, there is some optimization. So I guess we will study optimization towards the end of the class. But yeah, for much of this semester, we are not going to talk about optimization at all. But I do teach 5500 in autumn, where we talk about optimization of dynamical systems. So we touch upon those subjects there. Yeah. Any other question? Okay. So we have a robot. These are the states of the robot, like different links within the robot, what the state is going to look like. So it could contain angles, it could contain position vectors, and so on. This is the input, how you are running the motors within the robot. Yt is the output, which is how you are observing the state of the system. So many cases, Yt would be a camera sensor. So Y would come from a camera sensor. So this is actually a camera sensor in order to localize yourself within the space. Okay, so that's GJ mapping, and that again, many a times it could be a nonlinear mapping, or it could be a linear mapping. And then you have to process that image in order to come up with what the state of the system looks like, which is what your current state of the robot is at that point of time. So, so this is the model, and there are many special classes of these functions that leads to, which has sort of special names. So in shorthand, we are going to write it in this particular format: x dot And I do want to make a small note here, which is just trying to be pedantic about the notation. Much to my disappointment, the book is also using the notation x dot equals to f of t x u. I absolutely do not like this notation. Can someone tell me why I don't like this notation? I don't like this, I like this. Yes.
Like the x and u aren't we cannot conclude they are time dependent.
That's right. So x is a function from r to rn. So this is my time, this is my state space. This doesn't make any sense. This notation doesn't make any sense because f is a function that takes r cross rn cross rm to rn. It doesn't take r cross this is not our function. This is not the function. The function is this. And therefore, this notation is correct because now I'm evaluating x at a specific time, u at a specific time, and that's how I'm getting the derivative of x. So please do not use this notation. Do not use it in your papers. Do not use it in your assignments. Do not use it in your candidacy exam or defense. And certainly do not use this if I'm in your defense committee or candidacy committee, because you will hear my disappointment in your candidacy and defense. You don't want that to happen. Okay, so this is not a good notation. This is the notation, and we'll stick to this notation in the class. Okay. What is an autonomous system? Okay. So I'm stacking everything up in order to put this in a vector format. So this f is also in a vector format. So f contains f1, f2, f3, all the way up to fn. So is g. You are stacking all these functions up in the form of a vector. In autonomous system, so what is an autonomous system? This function f doesn't depend on time. It only depends on the current state. So the slope of x as a function of time is purely dependent on the current state, but it's not dependent on time. When I'm driving a vehicle, the dynamics of the vehicle doesn't depend on time. But if I were to fly a plane, my dynamics does depend on time. Why does it depend on time? Because I'm burning a lot of fuel. I'm changing the weight of the aircraft as I'm moving in the space. Okay, and in the context of a rocket, it's burning a lot of fuel. Okay, so rocket is really a time varying system. It's not a time. It's not an autonomous system, because in rocket a lot of things are changing very quickly. The density of the air is changing very quickly. The mass of the rocket is changing very quickly. So the dynamics is, and then rocket is also shedding a lot of weight as it goes into the orbit. So that's a system which is not an autonomous system, because it's changing very fast. But a vehicle is kind of sort of an autonomous system. Yes, we are burning fuel, but it's very little in comparison to the mass of the vehicle and the mass of the passenger. So that's an autonomous system. Periodic system, the state transition function, it has some sort of periodicity property. So for every x in Rn and for every t in R, it satisfies this expression. What's a periodic system? What's an example of a periodic system?
Pendulum.
Pendulum, for sure. Yeah. Anything else? Yeah.
Spring mass.
Spring mass. Yes, that's a periodic system. Actually, the spring mass itself is not a. I mean, the output of a spring mass is a periodic system, but that itself is, maybe that's true for pendulum as well. The dynamics doesn't depend on time in pendulum as well as in spring mass, so maybe that's not the right. Where the dynamics has some sort of periodicity. So a bad example, but if you look at the load on a Netflix server, it has quite a bit of periodicity, and it has two types of periodicity. One is the Saturday Sunday periodicity, so like a 7-day periodicity, and one is a daily periodicity. So after this class, all of you will go back and you will turn on Netflix and you will watch something, and all of that ping is going at the Netflix server. And so Netflix, from a Netflix point of view, if they have to manage their load, there is quite a bit of periodicity, and they need to manage that periodicity by either firing up more servers or shutting down servers, depending on people are going to sleep or people are going to wake up and watch something. Okay, so if you are going to go to one of these big tech firms, you will see a lot of periodicity in your dynamics because of the way how humans behave and because of the diurnal cycle. Same thing with Wi-Fi access points. They also see a lot of periodicity, because right now we are all in the room, our cell phones are connected, they are transferring data. So there is a bit of periodicity there as well. Okay, let's talk about LTV, linear time varying system. So f of txt equals to atxt. A maps R to Rn cross n. So A is a time varying matrix valued map. It's a linear system because xt is multiplied by a linear by a matrix, but this matrix actually changes with time. Okay, that's a linear time varying system. And then linear time invariant. So So right now, as you can see, I'm not really using the control actions right now, and we're not really looking at the observations. We are trying to simplify stuff for the time being so that we can study these things, and then we will make our life complicated as time progresses by adding control and whatnot. Okay, so we have ignored the control, we have ignored the observation, we are just looking at the evolution of X. We have various types of, like this is the full blown, without the UT, you have the full blown time varying dynamical system. Then you remove the time dependence, you get an autonomous system. You add periodicity, you get a periodic system. You have a linear system, but it's time varying matrix. You have a linear time varying system. You have linear time invariant system. And then you have nth order ordinary differential equation. So this is so I'm going to use the notation yit as di yt over dti. So that's the ith time derivative of y. And so the nth order ordinary differential equation, this is y and t is equal to h of t y0 t y1 t yn minus 1 t. This is nth order ordinary differential equation. So if I have, so y0, by the way, y0 of t equals to y of t itself. This is y of t. This is the first derivative of y, second derivative of y, n minus 1th derivative of y. That gives me this function yn. How do I convert this into this format? Without the u, of course. So we have this particular nth order ordinary differential equation. I want to convert that into this format. So let's look at how do we do that. So I'm going to define x1 of t as, if I'm not mistaken, yt. Yt x2 of t equals to y1t and so on. And then I have xn of t So this is the way I'm going to define my x. And then I'm going to define x1 dot t. What is x1 dot t? It's x2 of t. x2 dot t, x3 of t, xn dot t equals to h of t, x1t, xnt. So now I have converted this nth order ordinary differential equation into this sort of format. Okay, so these systems are known as autonomous systems. By autonomous, what we mean is there is no, not just autonomous, but Essentially, these are uncontrolled system. You're not controlling the system. The system is just behaving the way it is behaving. So you can think of ocean currents. They are behaving the way they are behaving. Nobody can control ocean currents. Nobody can control clouds. Nobody can control weather and so on. So we'll first start with simple systems that we cannot control, and we want to understand what happens in those systems. Any questions so far before we proceed? Either everybody understood everything or nobody understood anything. So let's hope that everybody understood everything. Okay, so we have a whole bunch of systems, whole bunch of differential equations. So I want to go over some theory of, maybe let's do some examples. Oh, I need to define what is a solution to these differential equation. Have I written it down somewhere? Oh yeah, initial value problem. So I have x dot t equals to f of t xt. My f is in C D R n. D is a subset of R cross Rn. So this is the time, this is time, and this is the state space. So this is the set of all feasible time and state spaces. So D is, let me just write it as set of all feasible time and state spaces. Okay. Generally speaking, we always talk in the generality of Rn, but in practical systems, you're not really going all the way to infinity and coming back, right? So it makes sense to define the function only over the set D, and it's giving out a vector in Rn, and then hopefully the set of states that are visited via this dynamical system lies within this particular set over a finite period of time that is of interest. Okay, so right, I am given that x of t naught is x naught. This is given, and my job is to predict this particular system. I want to be able to figure out what the solution to this system is going to look like. So we say define definition. So phi from R to Rn is a solution to this ordinary differential equation if and only if phi of t naught equals to x naught and phi dot of t equals to f t phi t. For some interval j containing t naught. That's my initial value problem. So somebody can cook up a differential equation with an initial value. And the question is, can we solve this particular differential equation? Can we identify a signal phi mapping from time axis to the state space, which is a solution to this? What do I mean by a solution? Well, it should start at t naught, phi should be exactly at x naught, and then it should also satisfy this differential equation. There is a phi dot here. Please note the dot here. So there is phi dot is equal to f for some interval j containing t naught. Generally speaking, we want, okay, in most situations, we are looking forward in time. We want to predict the system forward in time. There are some cases where we want to go backwards. We want to understand climate change. We want to see what happened 50,000 years ago. We want to see what happened 10,000 years ago. And hopefully that will tell us what's going to happen over the next 100 years, right? So in some cases, we want to look at the interval backward in time, but most situations that we would be encountering in this class, and probably you would be encountering unless you are a climate scientist, you would be looking forward in time. So this j should be t naught to t naught plus some epsilon c constant, or t naught to infinity, right? Just something to keep in mind, that you could have interest both ways. You can have interest backward in time, you could have interest forward in time. There's another place where you have interest backward in time when you want to do some causal analysis. So your system is misbehaving, you want to figure out what exactly led to that misbehavior. So then you might be trying to look backward in time, but generally speaking, we are looking for a solution forward in time. And the book generally is looking at solutions forward in time as well. So all the results that we are going to talk about will be forward in time. But if in case you are looking at things backward in time as well, then you might have to look at appropriate reference. This reference is not the reference for backward in time sort of behavior. Okay. So let's look at some examples. So I'm going to give, let me give you the first differential equation. So x dot of t, example, x dot of t equals to f of xt, f of x 1, x equals to 0, 0, x not equals to 0, and x naught equals to 0. So my t naught is 0 and x naught is 0. What is the solution to this differential equation? You know, it turns out that there is no solution to this differential equation. Okay, so like I said, this function should be continuous function. What I've given you is a discontinuous function. In fact, it's non-zero only at origin, and it's 0 everywhere else. And if you want to solve this differential equation, turns out you cannot really solve it, and there is no solution to this differential equation. So anybody can cook up a dynamical system function, but whether you can get a solution or not remains an interesting problem to study. Let's look at second example. X dot of t equals to xt raised to 1 over 3, x 0 equals to 0. This one has two solutions. So phi 1 of t equals to 2 over 3 t minus t naught, 3 over 2 t greater than equal to t naught, and phi 2 of t identically 0 for all t in R. So I have two solutions to this differential equation. So I give you a system, I give you a differential equation that describes that system, I give you an initial condition for that system. I really don't know which of these two solutions is the right solution. How is the system going to behave over the next few time instants? I can't say because I have two solutions here. It could be any one of them. Third is x dot t equals to xt square, x0 equals to 1. I have a solution here, phi of t equals to 1 over 1 minus t. For t minus infinity less than t less than 1. So I can go all the way backward in time, all the way to minus infinity. So I can go to the beginning when the universe was born. I can solve this differential equation. But I can't go beyond time t equals to 1 because this thing is going to blow up. This thing will become 1 over 0, it will become infinity. And so this term will no longer be, this differential equation will no longer be defined. Okay, we are starting from time t0 equals to 0. So what's an interesting problem here to study? So somebody gave me this differential equation. So what's an interesting problem here? So somebody gave me this problem statement. I have a dynamical equation. I have the initial condition for that dynamical equation. I want to be able to answer two questions, two important questions. Do we have a solution? Do we have a unique solution? Right? Do we have a solution? We have multiple solutions. We don't like multiple solutions because that changes our predictability. Do we have a unique solution? Okay. And how long is that solution valid for? So this is studied under the umbrella. So there are two results. One is, so two questions. Question 1, does phi exist? Question 2, is phi unique? So what conditions can I impose on this dynamical system and initial condition so that I have the existence of a solution to this differential equation? And the second question is, if a solution exists, is that the unique solution? Is that the only solution? Or are there multiple solutions to this differential equation? Okay, so that's what, by the way, until what time is this class? Is it 5:15 or 5:20? Do you know? 5:15? Okay. So I guess we are towards the end of the class. So I'll leave you with this thought. People who studied this back in 1700s and 1800s, does phi exist? Is phi unique? So we'll talk about Cauchy-Peano's existence theorem, which talks about, which answers the first question, but doesn't answer the second question. The second question was answered by Picard-Lindelof theorem. We'll talk about that, and then we'll talk about Picard iteration, which is the method of successive approximation to solve this particular problem. So those are the kind of stuff we'll be talking about on Thursday. Thank you so much, and see you on Thursday. Just give me a second.